When two planes intersect, the angle formed by two half-planes with a common edge, the line of intersection, is a dihedral angle. The angle shown in Figure 9.38 is such an angle. In Figure 9.38, the measure of the dihedral angle is the same as that of the angle determined by two rays that 1. Have a vertex, the common endpoint, on the edge, 2. Lie in the planes so that they are perpendicular to the edge. A polyhedron, plural, polyhedrons or polyhedra, is a solid bounded by plane regions. Polygons form the faces of the solid, and the segments common to these polygons are the edges of the polyhedron. Endpoints of the edges are the vertices of the polyhedron. When a polyhedron is convex, each face determines a plane for which all remaining faces lie on the same side of that plane. Figure 9.39a illustrates a convex polyhedron, and Figure 9.39b illustrates a concave polyhedron. As shown in Figure 9.39b, a line segment containing the two uppermost vertices lies in the exterior of the concave polyhedron. The prisms and pyramids were special types of polyhedrons. For instance, a pentagonal pyramid can be described as a hexahedron because it has 6 faces. Because some of their surfaces do not lie in planes, the cylinders and cones are not polyhedrons. Leonhard Euler, Swiss, 1707 to 1763, found that a number of vertices, edges, and faces of any polyhedron are related by Euler's equation. This equation is given in the following theorem, which is stated without proof. Theorem 9.4.1, Euler's equation. The number of vertices, capital V, the number of edges, capital E, and the number of faces, capital F, of a polyhedron are related by the equation capital V plus capital F equals capital E plus 2. Verify Euler's equation for the polyhedrons given in Figure 9.40a and b. A. Tetrahedron. Solution. The tetrahedron has 4 vertices, V equals 4, 6 edges, E equals 6, and 4 faces, F equals 4. So Euler's equation becomes 4 plus 4 equals 6 plus 2, which is true. Verify Euler's equation for the polyhedrons given in Figure 9.40a and b. B. Square pyramid. Solution. The pyramid has 5 vertices, vertex, plus vertices from the base, 8 edges, 4 base edges plus 4 lateral edges, and 5 faces, 4 triangular faces plus 1 square base. Now, V plus F equals E plus 2 becomes 5 plus 5 equals 8 plus 2, which is also true. Definition. A regular polyhedron is a convex polyhedron whose faces are congruent regular polygons arranged in such a way that adjacent faces form congruent dihedral angles. There are exactly 5 regular polyhedrons named as follows. Number 1. Regular tetrahedron, which has 4 faces, congruent equilateral triangles. Number 2. Regular hexahedron, or cube, which has 6 faces, congruent squares. 3. Regular octahedron, which has 8 faces, congruent equilateral triangles. 4. Regular dodecahedron, which has 12 faces, congruent regular pentagons. 5. Regular icosahedron, which has 20 faces, congruent equilateral triangles. 4 of the existing regular polyhedrons are shown in Figure 9.41. Tetrahedron, hexahedron, octahedron, dodecahedron. Because each regular polyhedron has a central point, each solid is said to have a center. Except for the tetrahedron, these polyhedrons have point symmetry at the center. Each solid also has line of symmetry and plane symmetry. Consider a die that is a regular tetrahedron with faces numbered 1, 2, 3, and 4. Assuming that each face has an equal chance of being rolled, what is the likelihood, probability, that one roll produces A. A number 1, B. A result larger than number 1? Solution. A. With 4 equally likely results, 1, 2, 3, and 4, the probability of a 1 is 1 out of 4. B. With 4 equally likely results, 1, 2, 3, and 4, and 3 favorable outcomes, 2, 3, and 4, the probability of rolling a number larger than a 1 is 3 out of 4. Another type of solid which you are familiar with is the sphere. Although the surface of a basketball correctly depicts the sphere, we often use the term sphere to refer to a solid like a baseball as well. The sphere has point symmetry about its center. In space, the sphere is characterized in 3 ways. Number 1. A sphere is the locus of points at a fixed distance r from a given point O. Point O is known as the center of the sphere, even though it is not part of the spherical surface. 2. A sphere is the surface determined when a circle or semicircle is rotated about any of its diameters. 3. A sphere is the surface that represents the theoretical limit of an inscribed regular polyhedron whose number of faces increases without limit. Each characterization of the sphere has its advantages. Characterization number 1. In Figure 9.42, a sphere was generated as the locus of points in space at a distance r from point O. The line segment OP is a radius of the sphere O, and segment QP is a diameter of the sphere. For the Earth, the equator is a great circle that separates the Earth into 2 hemispheres. Characterization number 2. The following theorem claims that the surface area of a sphere equals 4 times the area of a great circle of that sphere. This theorem treats the sphere as a surface of revolution. Theorem 9.4.2. The surface area, capital S, of a sphere whose radius has length r is given by capital S equals 4 pi r squared. Although half of a circle is called a semicircle, remember that half of a sphere is generally called a hemisphere. Find the surface area of a sphere whose radius is r equals 7 inches. Use your calculator to approximate the result. Solution. Capital S equals 4 pi r squared. Capital S equals 4 pi times 7 squared. Capital S equals 196 pi inches squared. S is approximately equal to 615.75 inches squared. Characterization number 3. The third description of the sphere enables us to find its volume. To accomplish this, we treat the sphere as the theoretical limit of an inscribed regular polyhedron whose number of faces, n, increases without limit. The polyhedron can be separated into n pyramids. The center of the sphere is the vertex of each pyramid. As n increases, the altitude of each pyramid approaches the radius of the sphere in length. Next, we find the sum of the volumes of these pyramids, the limit of which is the volume of the sphere. In Figure 9.43, one of the pyramids described in the preceding paragraph is shown. We designate the height of each and every pyramid by h. Where the areas of the bases of the pyramids are written, b sub 1, b sub 2, b sub 3, and so on, the sum of the volumes of the n pyramids forming the polyhedron is 1/3 b sub 1h plus 1/3 b sub 2h plus 1/3 b sub 3h plus ... plus 1/3 b sub n h. Next, we write the volume of the polyhedron in the form 1/3 h times the quantity b sub 1 plus b sub 2 plus b sub 3 plus ... plus b sub n. As n increases, h approaches r, and b sub 1 plus b sub 2 plus b sub 3 plus ... plus b sub n approaches capital S, the surface area of the sphere. Because the surface area of the sphere is capital S equals 4 pi r squared, the sum approaches the following limit as the volume of the sphere. 1/3 h times the quantity b sub 1 plus b sub 2 plus b sub 3 plus ... plus b sub n approaches 1/3 r times capital S, or 1/3 r times 4 pi r squared, which equals 4/3 pi r cubed. The preceding discussion suggests the following theorem. Theorem 9.4.3. The volume, capital V, of a sphere with a radius of length r is given by capital V equals 4/3 pi r cubed. Find the exact volume of a sphere whose length of radius is 1.5 inches. Solution. This calculation can be done more easily if we replace 1.5 by 3/2. Volume equals 4/3 pi r cubed. Volume equals 4/3 pi times 3/2 cubed. Volume equals 4/3 pi times 27/8. Volume equals 9 pi over 2 inches cubed. Just as two concentric circles have the same center but different lengths of radii, two spheres can also be concentric. Like circles, spheres may have tangent lines, however spheres also have tangent planes. As is shown in figure 9.45, it is also possible for spheres to be tangent to each other. Line T is tangent to sphere O at point P. Line S is a secant. Plane R is tangent to sphere Q at point S. Spheres T and V are externally tangent at point X. Each solid of revolution was generated by revolving a plane region about a horizontal line segment. It is also possible to form a solid of revolution by rotating a region about a vertical or oblique line segment. Describe the solid of revolution that is formed when a semicircular region having a vertical diameter of length 12 centimeters, see figure 9.46a, is revolved about that diameter. Then find the exact volume of the solid formed, see figure 9.46b. The solid that is formed is a sphere with length of radius r equals 6 centimeters. The formula we use to find the volume is V equals 4/3 pi r cubed. Then, volume equals 4/3 pi times 6 centimeters cubed, which simplifies to volume equals 288 pi centimeters cubed. When a circular region is revolved about a line in the circle's exterior, a donut-shaped solid results. The formal name of the resulting solid of revolution, shown in figure 9.47, is the torus. Methods of calculus are necessary to calculate both the surface area and the volume of the torus.